Hello everybody, so we are studying atomic and molecular physics. This is lecture 13 and now we are going to start electron spin, that is a new topic. What is the need to understand the electron spin? So if we don't understand the concept of electron spin, we won't be able to explain fine structure of spectral lines, and second thing, we won't be able to understand what is anomalous Zeeman effect. So, to explain fine structure of spectral lines, to explain anomalous Zeeman effect, we need to know the concept of electron spin. Now, let us try to first understand what is the fine structure of spectral lines. Now, we know that energy, when we talk about energy of the electron, it depends only on the principal quantum number n. N quantizes energy. So, that means if I talk about a transition, suppose this is n is equals to 3 level, this is n is equals to 2 level, and the transition is taking place from n is equals to 3 to n is equals to 2. In that case, for this particular transition, I should get a single spectral line. But experimentally, it was found that most spectral lines actually consist of two separate lines instead of a one. Ideally, I should get one, but instead of one, there were two spectral lines which were close together. And if you use a spectrometer with a very good resolution, then you can actually see two lines which are close together. That means the spectral lines revealed a fine structure. So if we are talking about that n is equals to 3 level is there, n is equals to 2 level is there, and the transition is taking place, we should get 1. Then how come we are getting 2? If the spectral lines have a fine structure, that means the energy level also has a fine structure. So, example of fine structure, if we talk about, if you take the example of H alpha line, which arises in hydrogen atom because of the transition from n is equals to 3 to n is equals to 2 level, it consists of two spectral lines which are separated by 1.4 angstrom. So, spectral lines possess fine structure. That means necessarily the energy level should also have a fine structure. And the spectral observations indicated that P, D, F, and other levels, they are double. That means those energy levels are double, but only S levels are single. So now let us come to understand what is normal and anomalous Zeeman effect. So we know that for each L level we have 2L plus 1 levels. So when an atom it is placed in a magnetic field, each L level it splits into 2L plus 1 sub levels. And so if the magnetic field is strong, then in that case whatever number of components we get, they agree with the experimental data. But if the magnetic field strength is weak, in that case the two values, experimental values and theoretical values, they do not match. So if we want to explain why this is happening, that whatever is happening in case of weak field strength, that is called as anomalous Zeeman effect. And if we want to explain anomalous Zeeman effect, we can do that only when we introduce the concept of electron spin. So what is, let us try to understand first spin of electron, and then slowly as we will progress, we are going to study Zeeman effect in detail. So we know that the earth, it revolves around the sun, and at the same time it also spins about its own axis. So you can actually compare electron with the earth in a similar fashion. Just like earth, our electron, when it is moves around the nucleus in its orbit, that time it spins about its own axis as well. So this concept of electron spin, it was introduced by Gaudsmit and Uhlenbeck. Now, what is Gaudsmit and Uhlenbeck postulate? When an electron moves around the nucleus in an atom, it also spins about its own axis with an intrinsic angular momentum that is independent of any orbital angular momentum that it might have. So we know that the orbital angular momentum value changes when the value of orbital quantum number changes, but the angular momentum which is there because of the spin motion, it doesn't change, it remains constant. That is why the name intrinsic angular momentum is given. So the magnetic moment arising due to spin reacts in a quantized fashion with the magnetic moment due to orbital motion of the electron, so that the spin can be either parallel or anti-parallel to the angular momentum. This we will understand when we will be studying vector atom model. Okay, so now we know that angular momentum L, it is L star H cross. In a similar way, we can write down spin angular momentum as S star H cross. We know that L star, it is under root L into L plus 1. In a similar way, we have a spin S star is equals to under root S into S plus 1. Here this S is called as spin quantum number, and here when we have done experiments, it was found that it has a fixed value. S is equal to half, and spin angular momentum has a fixed value. S is equals to root 3 by 2 h cross. Like L can take different values, but in a similar way, S cannot take different values. S has a fixed value for electron, half. Now the half integral spin is not to be taken as a quantum number that takes on different values like n and L. So n takes different values, L takes different values, but S has a fixed value. That is how it is called as inherent and fixed property of the electron. So Gaudsmit and Uhrenbach had postulated the concept of spin, and it was Dirac who was able to show its existence with the help of relativistic quantum mechanics. Now we have already studied about the space quantization of electron in terms of its orbital motion. Space quantization means in the magnitude as well as direction of the angular momentum, it is fixed in space. That is what the concept of space quantization is. When we talk about space quantization of electron spin, we have that spin angular momentum also has a fixed direction. So here we are going to define MS. Similar to ML, we have MS, which is spin magnetic quantum number, and it can take values from minus S to minus plus S, similar to ML, where it takes values from minus L to plus L. And here, as we have a fixed value of S plus half, MS can have either half or minus half value. And so the spin angular momentum, it will be root 3 by 2 h cross. Now here, the spin angular momentum will have only two orientations, one corresponding to spin half, another corresponding to spin minus half, half h cross and minus half h cross. So this is the kind of space quantization which you can see over here. This we have already discussed in orbital motion. In a similar way, we have it is for space. So spin has a fixed direction with respect to z axis, and it has only two orientations. So an electron spinning about its axis behave like a tiny magnet and possesses a magnetic moment due to its spin, just similar to the when it is moving in an orbit. It has a orbital magnetic moment because of the orbital motion, but we have calculated the value of orbital magnetic moment. But in a similar way, we cannot calculate the value of spin magnetic moment. And why it is so? Because we lack the knowledge of the shape of the electron and the charge distribution in it. We don't know how is the shape of the electron, how the charge is distributed in the electron, and so we do not calculate the value, but we just have to assign it a value empirically on the basis of experimental observations. So this value S equals to half, it is just assigned to the electron on the basis of experimental observations. And we will also calculate mu S, that is magnetic moment in terms of spin. That value also we are just writing it, it is an assigned value, not calculated one. So the spin magnetic moment of electron is oppositely directed to the spin angular momentums, just similar to mu L and L, they are directed oppositely. Here we have this factor 2 which is additional. The factor 2 in front of EH cross upon 2m was not there in the orbital magnetic moment, but it is required here in order to obtain agreement with the experiments. So these values are assigned so to match with the experimental data. And we know that when we define gyromagnetic ratio, it is the ratio of magnetic moment to angular momentum. So mu L upon L, that was EH cross upon 2m, that was the gyromagnetic ratio for orbital motion. In a similar way, here we have gyromagnetic ratio of electron spin, which will be mu S upon S, that is 2 times EH cross upon 2m. 2 times E upon 2m, because S star H cross will be equals to capital S. So gyromagnetic ratio of electron spin is minus E by m, and here it is minus E upon 2m. Here it is minus E by m, and in orbital motion it was minus E upon 2m. Now, here the additional energy acquired by the atom due to spin motion in a magnetic field is given by E magnetic equals to 2 times EH cross upon twice m into BMS, and in orbital motion 2 was not there, so 2 is extra here, and we know that ms can take only two values, half and minus half. So this is all about electron spin. In the next lecture we will study about the Stern Gerlach experiment.